In today's video I would like to introduce a very nice problem of Ireland Mathematical Olympiad, but I'm not sure which year this problem is. So anyway, we have the following information. Let p be a prime number and e and n positive integers. Our goal, we are going to prove if 2 to the p plus 3 to the p equals e to the n, then n equals 1. In the other words, we are going to prove we don't have the solution for this equation except if n equals 1, okay? Otherwise we don't have the solution. So that's the purpose of this problem. So the hint that I'm trying to give to this problem, try to use the binomial expression and expand it on the form of the product, because if you take a look at these two numbers, this one is written on the same form as binomial expression. Okay, if you're going to replace 2 with a and 3 with b, you will have a to the n plus b to the n. So that's meaning you are allowed to express this one on the form of the product if you have the exponent as an odd number. Okay, so the second thing, consider the cases, because you will have multiple cases here. Anyway, I would recommend to give the try to this problem prior getting into the solution. So I'm going to remind you about the binomial expression. We have a to the n plus b to the n equals a plus b factor e to the n minus 1 minus the second term will be minus sign, minus b is multiplied by e to the n minus 2, and all the way down to the minus a is multiplied by b to the n minus 2 plus the last term, which is b to the n minus 1. This one is happening if we have n is odd. If you have n is even, you cannot factor out this one. Okay, so I'm going to do the same thing on this one. I'm going to put 2 as a and number 3 as a b. This one, if p is an odd prime, okay, we'll have 2 to the p plus 3 to the p divided by 2 plus 3. Just I'm taking this term and divide it by this term. Okay, so I will have this one the same as 2 to the p minus 1 minus 3 is multiplied by 2 to the p minus 2, and so on and so forth until you get before the last term, which is this one, which is 2 is multiplied by 3 to the p minus 2 plus the last term, which is 3 to the p minus 1. Okay, this one is a congruent to p is multiplied by 2 to the p minus 1 mod 5. Okay, now we are going to prove this one. Okay, proof. So I'm going to put this one as a sum of minus 1 to the k, as k goes from 0 to p minus 1, of this term 2 to the p minus 1 minus k is multiplied by 3 to the k. Okay, if you expand this one, it's taking you back to this one. Okay, so if you replace k with number 0, we'll get 0 here, we'll get 0, which is 1, you get the first term 2 to the p minus 1, which is this one, is multiplied by 3 to the 0, which is 1 as a first term. So the second term will have minus sign because k, it will be odd. Okay, because it's taking k equals 1. This one is taking minus 1. With this minus 1 become minus 2 here. 3 to the 1 become this one. Okay, and so on and so forth until you get the last term. So this one exactly is the same as this one. I'm going to prove this one is a congruent to the p 2 to the p minus 1 mod 5. Okay, so we know 3 is a congruent to minus 2 mod 5. Okay, if you take in minus 2 to the left, you will have 5 is a congruent to 0 mod 5. That means 5 divides 5. Okay, I'm going to raise both sides to the k on both sides. Now I'm going to replace 3 to the k with this one. Okay, so I will have the sum as k goes from 0 to p minus 1 to the k. I'm going to expand this one as minus 1 to the k is multiplied by 2 to the k. Okay, then I'm going to take this value and replace it here. I will have minus 1 to the k is multiplied by 2 to the p minus 1 is multiplied by 2 to the k. Okay, now I'm going to put this one together. Minus 1 to the k is multiplied by minus 1 to the k. We'll have minus 1 to the 2k. Minus 1 to the k becomes even. That means this minus 1 turns 1. And also these two terms, 2 to the p minus 1 minus k, if you put them together as one exponent, we'll have 2 to the p minus 1 minus k plus k. K will be cancelled out. I will be left with 2 to the p minus 1. So this one, I will have 2 to the p minus 1. Okay? But don't forget, this is congruent. This is congruent to mod 5. Because I have reduced this one to the mod 5. Okay? So you have to do the congruent sign here. This one, if you take a look carefully at this number becomes a constant because it's not dependent on k at all. So now I'm going to take this 2 to the p minus 1 outside of this sum. So this one I will have as a congruent 2 to the p minus 1. It goes from 0 to p minus 1. If I'm going to expand this sum, I will have 1 plus and so on. I will have p terms of number 1 here. So this one is the same as 1 plus 1 and all the way down to the 1 mod 5. So this term, we have p times this one. That means this one is a p is multiplied by 2 to the p minus 1 mod 5. Is a congruent to the p is multiplied by 2 to the p minus 1 mod 5, which is this one. So we have proven this one. Now let's move on to our question. I'm going to break this one into 3 cases. So case number 1. So I'm going to, if p equals to as a even prime, because we have p as a prime, we are going to check when we have p as an even prime. So I'm going to plug this number of p into this equation to see what's given us. This one is given us 2 to the 2 plus 3 to the 2. If you calculate, this one is given us 4 plus 9, which is 13. 13, 1 as an exponent. So this one is verifying this one. We are okay. Now we are okay to go. Okay? Now we need to check when we have p as an odd prime. If case number 2, if p is an odd prime with n equals 1 always. So I will have this expression now. I will have 2 to the p plus 3 to the p equals a, because n is replaced with number 1 here. Okay? We know 5 divides this term, because this one divided by this one is giving us this expression, which is integer. Because since this one is an integer, that means 5 divides this term. Since 5 divides 2 to the p plus 3 to the p, which equals a, when we have n equals 1. Okay? We are okay. In the other word, 5 divides a. Okay? Let's check the third case. Case number 3. When we have p as a prime, when we have p as an odd prime, but n is strictly superior than 1. Okay? So by the way of contradiction, suppose we have a solution of the equation if n strictly superior than 1. Okay? With p as an odd prime. We know 5 divides this term, 2 to the p plus 3 to the p equals a, with n equals 1. Okay? This one is telling us 25 divides 2 to the p plus 3 to the p equals a when we have n strictly superior than 1. Okay? We can have a squared, a cubed, a to the 4th, and so on and so forth. Okay? Since 5 divides this one, that means 25 divides when we square this one, because 25 is a multiple of 5. Okay? So whatever the values of n here, 25 divides this one. Okay? Since 25 divides this term when we have strictly superior and 1, that means 5 divides this term, because this one is more powerful than this one. When we have a big divisor divides this number, That means this number is divide the same number. Okay, so that's what happened here. But this term is the same as this one, is a congruent to p to the 2p minus 1 mod 5. That's mean, in the other word, 5 not divides this term, because to have 5 divides this one, we must have 0 here. We must have this one is a congruent to 0 mod 5 here, but we don't have that. Okay, that's mean, but 5 not divide 2 to the p plus 3 to the p equals a. We don't have n strictly super than 1. Okay, so this one is a contradiction. This one is a contradiction. This means the contradiction. That's mean we don't have the solution for this equation when we have n strictly superior than 1. So we have the solution for this equation except when we have n equals 1. Okay, so I have done this proof. If you are interested in watching this one, don't forget to support us with your like and subscribe. Thank you for watching. I will see you in next video. Bye.